In this video, we graph the first and second derivative of a function. This is kind of a common quiz question. So you're given the graph of this function. It's not quite piecewise linear. It's almost piecewise linear, except we've got this little quadratic piece here. Basically, we're just trying to infer what the derivative is. Well, I think it's easiest to infer the derivative on the intervals where the function is linear. So we can look at this piece right here. We've got it's a line with a slope of rise over run is 3 divided by 2. So we've got a slope of 3 divided by 2 on the interval from negative infinity to this x value here, which is -3. So if I want to graph the derivative, the first thing I would do is I would graph the y value, y equals 3 over 2, because that's our slope on the interval from negative infinity to -3. So we'll start with that. And now the graph has a sharp corner here. We've got a slope of 3 divided by 2, or 1.5, as we approach x equals -3 from the right. But as we approach x equals -3 from the left, or excuse me, I said that backwards. As we approach -3 from the left, the slope is 1.5. But as we approach -3 from the right, we see that the slope is 0. So we've got a sharp corner there, so the derivative is not well defined. So we should put an open circle at that location. Then on this piece, our function is just constant. It's 3. What's the derivative of a constant? It's 0. You can also tell that it's a horizontal line segment, and that has a slope of 0. The rise over run, we go up 0 and run to the right 3. So it has a slope of 0. So the derivative value on this interval from -3 to 0 has to be 0. So we'll graph that. Now on the left endpoint, again, we had that sharp corner. We had different slopes on the left and the right of -3. So we will plot that point as an open circle. But here, notice we've got a parabola, part of a parabola, meeting our y equals 3 line segment. This actually does have a slope of 0 at the top. As we approach x equals 0 from the right, the slope is approaching 0, and as we approach x equals 0 from the left, the slope is 0. So the point 0, 0 is actually on our graph. If we want, we can color in that circle, just labeling it for, or not labeling it, but just drawing it for emphasis. And then on this piece, we can think about that parabola. I'll look at it. It looks like you've got part of a parabola that has been shifted up 1, 2, 3 units. And it's got just the traditional shape of a parabola with a coefficient of x squared. As we go to the right 1 unit, the y values go down 1 unit. As we go to the right 2 units, the y values go down 4 units. So you're going down 1 and then 4, and then the next one would be 9. Every 1 unit change in the x direction, we square that number that we're changing by, if that makes sense. So this is x equals 3 minus x squared, which gives us that piece. And the derivative of 3 minus x squared is -2x, just using our basic rules. So our function has a slope of -2x on the interval from 0 to 2. So we can graph that. Y equals -2x. And we want to make sure we're on that interval. And then notice we've got an open circle there. So we're going to have an open circle on our derivative graph as well. So we'll plot that point, x equals 2, y equals -4. That's the value of -2x at x equals 2. So that should be an open circle rather than a closed circle. And then on this piece, we see we've got a line segment. And if we also can see that if we were to continue that line, it's actually a ray on the interval from 2 to infinity. If we continue that line, it would actually pass through the origin. Starting at this point, if we go up 3 and over 3, we find another point on the line. So this line has a slope of 1, or you can go up 1 and over 1. So the rise over run, or the change in y over change in x, is just 1. And if we go sort of work backwards, sort of guessing what the rest of the line would look like, we see that that line would have passed through the origin. So this is just the line y equals x. y equals x has a slope of 1. So we'll graph y equals 1 on the interval from 2 to infinity. And make sure that that point is actually not included. Actually, the derivative from the right of x equals 2 does exist. I think we can color in that point, actually. The derivative from here, the derivative from the left exists. It's 3/2, and the right exists. The limit from the right, or the derivative from the right exists, it's 0. But since they're not the same, we got open circles there and there. As the derivative of the original function is not well defined. Then on this piece, everything is good. Everything is good. That open circle is not included. If the function's not continuous at a point, it's not differentiable there. Oh, okay, well, we're saying, provided that we're using that rule, if the function's not continuous, it's not differentiable. That actually should be open. Sorry about that. I had to think through that for a minute. Alternatively, if the function was only defined on the interval from 2 to infinity, then we would say it is differentiable from the right, and we'd be able to include that point. But because the function is defined for all real numbers, at points of discontinuity, the derivative does not exist. So this purple graph is our derivative function. And that's it. Now, if we want to take the second derivative, we can. The derivative function happened to be piecewise linear, and most of the pieces have a 0 slope. This is a horizontal line, so it has a 0 slope. This is a horizontal line, it has a 0 slope. This is a horizontal line, it has a 0 slope. And this is a line with a slope of -2. So the value is -2. So when I graph the second derivative of this original teal function, I'm just graphing the derivative of this purple function. It's relatively simple. We're just going to hit 0 from here to here, and then we're going to skip the point when x is equal to -3. And then we're going to get 0 from here to here, and then we'll skip this point at x equals 0, y equals 0, because the slope from the left and the right of x equals 0, well, they're not the same. As we approach 0 from the left, the slope is 0, and as we approach 0 from the right, the slope is -2. So we're going to get 2 values from the left and the right, so we have to have an open circle there. Then the value of the function will be -2 on the interval from 0 to 2, not including the endpoints, and then it'll be 0 again. So that graph looks like this. And we should add some open circles everywhere. And that is the derivative of the purple graph. Now you can't really see the purple graph because we drew the derivative over it, but that is the derivative of the purple graph. Now, sometimes you're given a problem where you're given all 3 graphs at the same time. This is not an example of that. It would almost be an example of that, but parts of the purple graph are hidden by the graph of the second derivative. Sometimes you'll be given a graph and it'll say, here are 3 functions. One of them is f, one of them is f prime, one of them is f double prime. Which is which? And you're supposed to identify which function is the slope of another one. So what I usually do is I just focus on one particular function and then think about its derivative and then identify which of the other 2 functions could possibly be that derivative. So I might focus on the purple graph and say, okay, given this purple graph, well, what is the slope of that? Well, it's 0. Well, the only function that's 0 on the interval from -infinity to -3 is this blue graph. So this blue graph must be the derivative of the function in the purple graph. And then you say, okay, well, how does that relate to this one? Well, this is a line, this teal one. It's a line with a slope of, rise over run is 3/2. So it's a line with a slope of 1.5. So you take your 1.5 and you say, okay, well, if this is a line with a slope of 1.5, is there a function that is just equal to 1.5 on that or on that interval from negative infinity to 0? Excuse me, negative infinity to -3. You say, yes, this one is. So the teal graph must be the original function. The purple graph must be the first derivative, and the blue graph must be the second derivative. And I was able to infer all of that just from looking at the interval from negative infinity to -3. And that's also assuming that's provided that that pattern is consistent on the interval from -3 to 0, on the interval from 0 to 2, and then on the interval from 2 to infinity. So once I decide that I'm pretty sure that this is the function, the purple graph is the first derivative and the blue is the second derivative, then I look at each of the other subintervals of our domain and then see if those labels that I placed on the graphs are consistent from sort of branch to branch of this piecewise function. So that's what I would recommend. I would recommend trying other problems like this. There are problems like this in the homework. Just get as much practice as you can. This is a very common quiz question where I give you the function and I ask you to graph the first and second derivative, or I give you the first derivative and ask you to graph the original function and the second derivative or something like that. So we can go in both directions, either from the derivative to the original function or the derivative to the second derivative.